Now, can you hear? Okay, thanks. So let me first thank the organizers, Pierre, Lochak, Devendra, Tiwari, for organizing such a nice discussion meeting on a very rich subject where I learned lots of things. And I'm also glad to meet lots of old friends and make some new ones. So I will talk about the contrast and analogies in function field situation. And if I want to give a punchline, I would say that in his language, we will see that in spite of some big contrast, the linear theory with motives and unipotent part works mysteriously well. But you will see that slowly. First, I will start with just what is the basic things about analogies of function fields and number fields. So instead of thinking of rational numbers, integers, their completion like real numbers and complex numbers, the notation, I mean, you look at rational functions, polynomials, the completion with the usual degree absolute value is the Laurent series. So I usually will call this K, A following the Drinfeld, and then this is K infinity, completion at infinity. And this would be C infinity, which in this non-Archimedean situation, K infinity bar completion. So the one big difference is this algebraic degree is 2, this is infinite. Now this will be in characteristic P. There is another analogy is the units, if I look at Z star, that's just plus minus 1. So cardinality is 2, whereas A star is FQ star, and the cardinality is Q minus 1. So often Q minus 1 will play a role of 2. So the even numbers will be multiple of Q minus 1. So Q minus 1 multiples are called Q even here. And I will, most of the talk I will do that, but most of the theory can be done with any function field. Then you have to choose an infinity. Here it's God given, so to say. Once you choose an infinity, this will be the coordinate ring for curve minus that infinity, and then again the completion and like that. And you can introduce several infinities when you are in multi-dimensions. But I will be first in this setup. And first thing I want to say is just a perspective of this. So there are number fields and function fields over any constant field can be characterized by having the notions of sizes or absolute value connected with the product formula. This is the theorem of Artin and Waples. So product formula with absolute values is number fields and function fields. And finite field is much better than any other function field because the residue fields are finite. And then that arithmetic comes up. And that's why these are called global fields of characteristic P or characteristic 0. So these are global fields. So whole algebraic number theory and class field theory can be sort of, so to say, developed in parallel. And this was done by Artin, Tate, and Waples, and so on. And the main thing, and there is a lot of going back and forth. So I just want to give a couple of examples, and then I will move on to real things. So if you think about Riemann hypothesis, that's number theory. Weyl transferred it to this setting and did Weyl conjectures. And they were so successful, but he was working over FQ bar. They were so successful that Iwasawa again turned it back into Iwasawa theory, which Sujata talked about. Sujata talked about Iwasawa theory. That was built on analogy that if you go from FQ to FQ bar, you're basically joining all the roots of unity to get geometry. So way to get number theory, some geometry and some cohomology modules and so on. He used roots of unity and cyclotomic extensions or more general ZP extensions, right? I mean, so the Galois group being cyclic, profinite cyclic played a big role in Iwasawa theory. So there is a back and forth between, and he went into some different p-adic thing. But anyway, there is a second such thing was Mordell conjecture. Mordell conjecture was made for Q. The Russian school, Parshin and so on, proved it for function fields. Faltings took up their ideas of Parshin and so on and made one proof in number fields, some ideas, and same thing with Wojta's proof, which used Arakelov theory ideas. So again, it went back. And the Langland's conjecture is the third thing. I mean, there are many, but Langland's conjecture similarly, first Drinfeld, the elliptic curve thing, Drinfeld generalized. So those objects will come up when I talk about these things. He did the geometric thing, and then that was again transported lots of things which Drinfeld did with Stukas and so on, came up in the p-adic Langlands or geometric Langlands and so on. So there is a lot of back and forth. I will just mention same thing with Birch and Dyer. There was a work of Tate, and then back to Perrin-Rieu in p-adic case, and so on. Stark conjectures is a similar story. I mean, we have expert Mahesh here in the sort of Iwasawa theory and Stark conjectures there. But so there are lots of analogies between number fields and function fields. So, but now let me start talking about, there is a big difference. In characteristic 0, this is a prime field. In characteristic field, prime field is FP. That right away shows up in Nakamura's talk. We saw that Grothendieck's program started, he got big inspiration from Belyi's theorem. So Belyi's theorem actually, if you think in characteristic P, it was known in 1950s, much before Belyi. This was done by Abyankar, and Abyankar proved that instead of P1 minus 3 points, if you have anything over FP bar, then it is ramified at 1 point, except you use wild ramification, right? So Abyankar had written down this map. I mean, so if you have something over FP finite field, FP bar means finite field, you can kill the finite field by that. And then 0, 1, and infinity, you can, 0, infinity, you can kill by x goes to x to the q plus 1 over x. So that's Abyankar wrote this down. This was again in the seminar, Bourbaki Katz thought that he independently discovered, but then he realized, actually, I told him, in fact, that this was done by Abyankar in 1957. So now, if you look at the fundamentals, so Belyi's theorem works for over prime field, so it's not a function field you are getting finite field. Okay. Second comment is, and finite field, the Galois group is too easy. G of Q is just G hat. Right? Now, if you look at the fundamental group comparison, Grothendieck's comparison theorem actually connects it with the tame fundamental group. So you can do with tame ramification, you can do P1 minus 0, 1, infinity, but it's still the different story. It's not a function field. Right? So I will, before coming back to the function field, what happens? I mean, so the GK and GQ is, if you are interested, this is sort of not doing that. This is because the prime field is different. Right? Another comment I want to make is, we looked at the tangential base point and Puzo series. I forgot in whose talk, Nakamura or maybe your talk and so on. So the Puzo series don't give the algebraic closure in this case, right? So this was again, it was known, but Abyankar noticed that if you look at the K infinity, instead of Newton's theorem that the algebraic closure is the Puzo series, what you get is what is called, it's a more complicated K infinity bar, and it's what is called Hans series. So you don't, you just don't have the denominators need not be bounded in the thing. So and it's a complicated thing, and that's not an algebraic closure. You have to cut it down. There were some papers by Kedlaya. You can cut it down by algebraic equations, but there is a connection between algebra and automata, and the automata style of things which was used to give another description by Kedlaya. Okay, so there are, in the basic things, there are some differences. But I want to now start with the simplest thing, Abelinization. So I will start with the cyclotomic theory. Right, so I'm going to talk about cyclotomic theory first. And so cyclotomic theory, usually you have Q e to the 2 pi I over n. And the Galois group is Z mod n Z star, and you have Kronecker-Weber theorem and so on. So I want to do the parallel for that. So I will introduce what the exponential is. So the idea is like that. You think about these things are just torsion of endomorphisms of multiplicative group where n goes by nth power map. So Drinfeld and Karlitz before that, they didn't exactly say it in this language, but Z, the analog is A, which is the polynomial ring. So you look at A. I am not going to explain right now, but the correct group here is additive group. And there are fewer multiplicative functions, but somehow there are more additive functions because of the Frobenius or pth power map. So if I use this over some end of F, this is F tau, where tau is pth power map, and it commutes by, it's a non-commutative ring because it will sort of, there is a commutation relation using pth power. And I'm just going to write down, and I'm not going to explain, I can explain it later. I will just write down T goes to, so T goes to the map, X goes to, so X I use, all right, Tx plus X to the Q. This is called a Drinfeld module or Karlitz module of rank 1. And just like you have an exponential which says e to the nz is equal to e to the z to the n, this looks a trivial thing, but that is the functional equation. Notation makes it look trivial, but exponential of nz, So the action of integers is given by a monomial here. The same thing happens here. Now it's action of, this is any polynomial in A. This turns out to be polynomial. This is a polynomial, Cartesian polynomial or Drinfeld polynomial in EZ. So there are functional equations like that. So in particular, E of TZ would be T of EZ plus EZ to the Q. And the point is there is, and then there is an exponential. So this is the exponential. Once I normalize the first coefficient, this is the exponential. And then once you have K, you can do K. So I mean, classical Iwasawa theory, you had K adjoin the usual roots of unity, zeta n, right? And if you take, so without loss of generality is Q to the R minus 1, and then it's Z mod R is the, so the Galois groups in the Iwasawa theory were parameterized by the usual integers. Here the Galois group would be e to the, so I forgot to say the kernel of exponential is, there is some transcendental number in C infinity analog of 2 pi I, and it's like 2 pi I Z, just like here the kernel, except you are going from additive group to multiplicative group. Here it's 2 pi I Z. So there is an analog, I denote it by pi tilde, and this is the kernel, so it's a rank 1 lattice. And then what, yeah. Yeah, what's the question? I am saying that there exists a function which satisfies this functional equation. There is a unique such function. It's actually FQ. I'll just write it down. So E of Z is summation Z to the Q to the N over Dn, where Dn is product of T to the Q to the N minus T to the Q to the J, 0 to N minus 1. That's it. That's the function. This is an entire function which converges completely on C infinity. So that's an entire function. Okay, just like exponential of Z is summation Z to the N over N factorial. These are like factorials. Okay, and you see that those things are like finite field polynomials, right? So this is a function on this C infinity to C infinity. It's an entire, and the main point is algebraic. It satisfies this family of algebraic relations. So there is an A action for which it's a function. No, so that's the funny thing. This was done in 1930s by Karlitz, and then it was forgotten. And that is, Karlitz did it in the global case, and Lubin-Tate in 1970s did this in local case. And Hayes, who was a Karlitz student, was a postdoc at Harvard. So when Tate lectured on it, he said that I saw these equations in my course many years ago. Then they looked at the papers and found out that Karlitz actually had done those things, and it was forgotten because his paper was called Some Polynomials in over Finite Fields. When he proved class field theory, it called class of polynomials. When he proved Mahler's interpolation, it was called a set of polynomials. So Tate said he gave such unimaginative titles that nobody read it. So yes, in some sense, derived class field theory means, so what is class field theory? So usually that's what I am writing here, right? Your N torsion generates the abelian extensions. This N torsion coming from this exponential or this action is generating this thing. The Galois group is very similar. It acts very similar things. So e to the pi tilde over A, this is like e to the 2 pi over N, right? But these are parameterized by polynomials now. This A is a polynomial. So there are two kinds of cyclotomic families. One is parameterized by integers, one is parameterized by polynomials. Okay, and there is a Kronecker-Weber theorem which I will not state, but it's basically combining this, you get all abelian extensions. Okay, now having A is arbitrary, right? For A is in A. No. Okay, so right now I am doing this, but this generalizes to any function field. But then of course you have to change equations and so on, right? So this is, I am just doing everything for FQT. Whole thing is developed in general, but it just needs more preparation. Okay, so that's it. So there is a Kronecker-Weber theorem. So abelian extension. So what does that mean? So first of all, group theoretically, this is quite different than that. If you think of Z mod P to the N Z star, they are basically cyclic, right? Per P odd, and you get these ZP extensions. If you look at this and complete A to the P, P to the N, AP is one AP, so you get AP kind of Galois extensions by this, but AP is countably many copies of ZP, right? So AP star is, countably many copies, and then there is a finite part, many copies of ZP, where P is the characteristic, 1P, okay? And the point is, the ZP star on the other hand is, so if you look at GQ, now AB, there are so many computers. The correct abelianization here, so GQ AB, there are, the talk we here or there, you have to think, on the front of the board. So GQ AB is just Z hat star, right? Because of this, because you are just taking inverse limit. And that is product of ZP stars. And that is basically copies of ZP and Z mod P star. So you understand the sort of which finite groups come up, and otherwise it's like a propy complete cyclic groups and so on. On the other hand, if you look at GK-AB, because of this, there are lots of ZP extensions rather than a unique one. And then there are, for that P, for other P's, it's different. And the finite groups are very complicated depending on what Q is and so on. So what finite groups occur is also different. Yeah, lots of things come up in there. Yeah, but so, this takes care of everything. Okay. Leopold conjecture. So for P, there is a P. I forgot exactly. It's known for. Yeah, I can. Kisilevsky worked on it. So Google him. I don't remember exactly what the thing is. So this is the sort of explicit class field theory. So the point is, this thing can be done. So instead of this rank 1 lattice, you can do rank n lattices. And that's the point here. In here, this degree being 2, you can just do rank 1 and rank 2. So multiplicative group and elliptic curves. And so you get representations in GL1 or GL2. Here you get, you can have rank n lattices, and you can again do the exponential function. Exponential function has a product formula, which is basically product of 1 minus z over a, where a belongs to the lattice minus 0. So it's like Weierstrass function kind of thing. These things automatically satisfy such functional equations and give you Drinfeld module. And over C infinity, just like there is a lattice and elliptic curves correspondence, there is a Drinfeld module and lattice correspondence. So this is a rank 1A lattice, right? So you can take rank n lattice. So this I will write lattice lambda, which is just discrete A module in C infinity. So it's a co-compact kind of thing. It's a usual kind of lattice. Now it's in C infinity, and this C infinity has room for any rank. So you get a Galois again from the torsion. You will get, instead of GL1 A mod A star, you will get GLN representations. And Drinfeld, using the elliptic curves analogy in number fields, had a program to do GLN using the moduli space of these things. And basically he did it, except there are compactification issues and so on, which took long time to resolve. And Laforgue and Drinfeld did GL2, and then Laforgue did everything. There is one more critical just point here. You choose an infinity in general function fields. So you need to get everything, you need to change infinity at least once. So you have to use 2 infinities to get everything. That is just a technicality. I am just going to ignore that. Okay, so these are Drinfeld modules, and the Greg-Anderson. So there are also something called Stukas, which include Stukas use all the infinity at the same footing. That's the technically sort of much better. Stukas have been used recently by Scholze in p-adic thing. So again, he uses the Drinfeld's analogy, and now he's going back to function fields to number fields. So there is a lot of such interaction, which makes it very interesting. All right, so now I want to say a few more things about this. So then Greg-Anderson, so he realized that there is a way to get motives out of this. So these are really motives. They are what he called T motives. T was some endomorphism of the additive group, and basically if you have a bigger ring, you just have extra endomorphism like complex multiplication. That was the thinking. So these are motives. I'll just say, and I'm not going to even define these things very carefully, because I want to get to more to things which were so K. These are some modules over KT tau. So it's some non-commutative ring. So M is a module over some field F T tau. This is a non-commutative ring. So Drinfeld, by the way, so this thing was, Drinfeld already, this is a non-commutative thing. So there is a commutative subrings of a non-commutative ring. There is analog of that is a differential operators and commutative subring. This was a Kirchhoff dictionary. Okay, and there's a Drinfeld and Kirchhoff had this kind of algebraic geometry dictionary, which will come up in this arithmetic game too. So Greg Anderson developed this thing. He answered some questions of Drinfeld. There was some duality Drinfeld had missed at earlier when he did some correspondence to the lattice and so on. And so this is with some conditions. I'm not going to write them down. So once you have that, you have tensor product. So you can take tensor product, for example. Now this C, this is the Karlitz module, which is this action, or you can think of this. This plays analog of Z1, the Tate twist motive 1. So once you have a tensor product, you have C tensor N, which plays the role of Tate motive N. And what am I saying? Why am I calling it motive? There are no cycles or criteria as such, but this is a motive in a sense that there is DRAM realization, Betty realization, crystalline realization, all kinds of realizations with functors and with comparison maps between them. For example, this would be like the lattice would come from the Betty realization and so on. And those realizations can be done by, so to say, linear algebra operations. So you have much more control than usual. So you don't need the cycles and unproven statements on cycles. This forms a Tannakian category. So there is some notion of purity. So there are pure motives and there are mixed motives, and some categories are well defined. There are lots of variants. But this is, for example, and there is a dimension and there is a rank. So the Drinfeld module world is just, whole thing is one dimensional, because all such Drinfeld modules, it can be shown they correspond to, at least over C infinity, they correspond to C infinity modular rank 1 modular lattice of any rank, right? So there is a correspondence like that, lattice of any rank. So that's one dimensional. If you want to do C infinity, like move from elliptic curves to abelian varieties, there are some issues. You have to be looking at the pure ones, uniformizable ones. So there is a lot of technical things. The conditions about those are more complicated. In dimension 1, everything is very simple. So that Greg Anderson figured out about which things are good and so on. In dimensions, so there is a dimension and a rank. The rank is a rank of a lattice if you are over C, but in terms of these equations, this is Q. If it was Q square, I would call it rank 2. Okay, that's how rank works algebraically, and it will respect in the lattice here. This is a principal ideal ring, so that's much easier, but in general, it gets slightly more complicated. Anyway, so this is a pure motive, pure in a sense, the Frobenius eigenvalues, pure in sense of cohomology and weights. So there is a yoga of weights, there is a mixed Hodge theory kind of things. So a lot of parallels exist. So pure motive of dimension n and rank 1. Okay. And what is the zeta function? What is the zeta value now? So I mentioned that Weyl looked at the zeta, but that's the thing which algebraic geometry gives, and that's a rational function in Q to the minus S. So we look at Karlitz zeta. So this was, Karlitz didn't say it's a zeta, but he looked at this series. So S is summation 1 over n to the S. So usually you put n greater than 0, and that translates to, so A, instead of integers, I should put polynomials, and positive would mean A monic. So you choose a T. Once you choose a T, you get a sign, and you choose a sign 1. So A monic, this thing converges for S greater than or equal to 1. So even zeta 1 converges, because you are in the Archimedean situation where the term tends to 0 in this topology in K infinity. So, and Karlitz proved, so this is Karlitz-Euler type result. He proved that zeta of C of Q minus 1 S is pi tilde to the Q minus 1 S times rational. And there is a lot of number theory in that rational. There are Bernoulli numbers, there is a factorial, there are Herbrand-Ribet theorem. So lots of classical cyclotomic theory is included here. So it's a very parallel situation. So the interesting thing is what happens for the odd ones, right? Because that's a big problem. We don't know anything about the odd ones in the classical case except like zeta 3 is irrational and so on. So what we could do, so Anderson and I, this was done long ago. So Anderson and I had a paper in 1990s where we gave an algebraic incarnation to all of these zeta CS. Okay, so we proved, so there is algebraic incarnation. So algebraic incarnation using logarithms. These things have exponential and logarithm, just like this action. You use this action and you get exponential logarithm for on C tensor S. In other words, these are periods of extension given by C tensor S to trivial thing, and that extension is given by Deligne-Soulet cocycle. Okay, so now I am connecting to, as you will see, I'm slowly connecting to the things we were talking about. So Deligne-Soulet cocycles they come up with, in the zeta theory like that, they come up with the K theory, which we miss, but they come up in a cyclotomic modules theory, which is also connects here. So we have a cyclotomic module theory, and Deligne-Soulet cocycles can be explained in those terms. They connect here also. This is a C tensor S, and as soon as, so these are periods. Once they are periods, so actually the way first this is a pure motive. There are periods of a mixed motive, which is the extension given by Deligne-Soulet cocycle. So this is through log, I will say. Now, if you just think of classical transcendence theory of log, that works not only for classically, but whenever you have group and log, is the Hermite-Lindemann theorems work. So that means this implied that all of these are transcendental. Not only that, we proved that this is torsion if and only if S is even. So this is Anderson and myself, Greg Anderson. Torsion if and only if Q minus 1 divides S. So that implies that zeta CS is transcendental, and even zeta CS over pi tilde S is transcendental if S is odd. Right? So this is something you would like to know, whether that happens. So this is transcendental, and this was done by, so this is like using, as I said, using the Hermite-Lindemann theory. This was done by Jing Yu. So consequence of that, using the Hermite-Lindemann theorem on these T motives. But then the transcendence theory was developed more, and the Grothendieck's conjectures on periods was proved. So what is that? That says that if you have relations between periods, algebraic relations between periods come from algebraic relations between motifs themselves, whose periods are there. So that implied, so the things, so this is, I will just write some name, Anderson, Brownawell, Papanikolaou. So you develop the Tanakian theory of these motifs and use their criteria, and what you get, so because of this conjecture, you are basically looking at some motivic Galois group and just computing its dimension, and that gives you transcendence degree. So that's a machine to compute linear independence. So the result, final result is, so these are the old results. Final result is all algebraic relations between the zeta values, zeta S, come from this one, come from this, or there is one more extra, which is there is no parallel in classical case. PS is zeta C S to the P, which is obvious because you're in characteristic P, so P is additive as well as multiplicative homomorphism, pth power, right? So those are the only algebraic relations. There are no more algebraic relations between these quantities. Yeah, this is a theorem. No, this is a theorem. That's what I'm saying. So this would be a conjecture in classical case. This was a theorem, and it uses exactly what we proved. But that, I mean, transcendence theory, earlier it was Hermite-Lindemann, then it was a Grothendieck conjecture, the transcendence theory, and that implies this. So, yeah. Okay, so that's a theorem. Yeah. So there are exponential logs, multipolylogs, and so on. So C tensor S has a logarithm, and that has like a canonical coordinate, which is basically multipolylogarithm. Sorry, not multipolylogarithms. I'm doing multi-zeta values, so I sometimes. So polylogarithm theory is there. So there is an expression in terms of polylogarithms. That's another way of doing that. And I will come to that when I talk about multi-zeta values. So I will say here that, so there is a divergence between harmonic series and the logarithm, because it's the logarithm is z to the n over n, but it's not z to the something over a, because there is no z to the a. So there are some divergence already at that level. Okay, so that's one thing I wanted to mention. So then we developed. Chanuel conjecture is not known. Not known. So now I want to say that there is also, so I will just say this, and I'm not going to define this. I defined gamma functions. We can interpolate this at periodically. Gamma function can be interpolated periodic. I defined Gauss sums and Jacobi sums by mixing these cyclotomic theories. And there is even a Gross-Koblitz formula I could prove without crystalline cohomology, directly using Stuka kind of ideas. And there is a lot of geometry. So for FQT, it works exactly like classical case. And for higher genus, the geometry of theta divisors controls which primes occur in the Jacobi sums and Gauss sums. So it's a very interesting geometrical thing, which connection with the Stukas and so on. But so I define also hypergeometric functions, and there are some results on those. I just want to say that there is a rich transcendence function theory. That's all I want to say with that line. So now we are going to start with the multi-zeta story. And the multi-zeta story, as you know, comes from the pro-unipotent part of the GT when you compare Dirac and Betti. So I'm going to show you how the Dirac-Betti story works almost the same without having the original object. So we have no clue what profinite story is even. So we are taking profinite, but when you go to the mixed motives and multi-zeta, it works. Or we also do the meta-ability. So Nakamura talked about Ihara power series. And I will also state the things about Ihara power series, and all the objects which he talked about, there is a complete parallel in the function field case. So those two things are connecting extremely well. So I mentioned lots of contrast and a lot of things which happen, right? Now I'm going to say multi-zeta value theory, and there are lots of analogies. So let's see. So I will first define the multi-zeta value. Okay. So multi-zeta value I will define. So let's recall the classical case, zeta S1. So I will have, maybe I will use the reverse normalization. So S1 to Sk is usually, for me, it is 1 over N1 to the S1, Nk to the Sk, and N1 is greater than N2 greater than Nk, and that's greater than 0. So, and there is some condition about first or last coordinate to be 1 for convergence, because in the other talk sometimes this order was reversed. So I don't want to get into this in front of the board. So that's a real number. That's the usual multi-zeta value. Here, what I define is, so there is no natural order on integers, right? So there is a partial order using degree. So instead of greater than 0, I would say sign is 1. And instead of this greater than that, I would say degree of this greater than that. That's how I'm going to define. Okay, so zeta S1 to Sk I defined by saying that A1, degree of A1 greater than degree of Ak. And this thing I changed to sign of Ai is 1. Okay, and then same thing, 1 over A1 to the S1. Ak to the Sk. So now is in K infinity, which is the analog of real numbers. Okay. So first thing, so see the things are in function field case, this is clear that this is non-zero because you are adding positive things. So that's non-zero. It was a hard theorem for me to prove that this is non-zero, because here in a function field, things can cancel. Right? If you add anything p times, it's 0. And there are other ways of canceling things. So this is a non-zero thing. So I proved that. That is the first step to prove transcendental. Now it's known to be transcendental for all of these because of period connection result of Cheyu Chang, and I will mention that. But let me go beyond this. So immediately you will see that you saw this proof that, so I'm just using the same notation because I don't want to change the notation, right? This is function field, that's number fields, okay? In this case, you saw that, right? Zeta A times zeta B was zeta A plus B when N1 is equal to N2, and then zeta AB plus zeta BA, just because of that order of in Z. Things are ordered. So if I take 2 copies, the index in the 1 copy is more or less or equal, right? That's how the sum shuffle works. That itself breaks down, right? Because there are too many things of the same degree. So it was not clear for a long time whether this satisfy any shuffle relations, but eventually I showed that they satisfy shuffle relations, and the shuffle relations are universal. That means they not only work for FQT, they work for all these things. So the theorem I proved was that this product of multi-zeta, so these are the MZVs, product of MZVs is sum of MZVs. Sum of different MZVs, sum of other MZVs, preserving weight and preserving weight exactly. So weight is as usual the sum of the indices, preserving weight and depth filtration and filtration in depth. But sum means what? You are adding 1. So you will end up in a prime field. So all these relations have coefficients in a prime field rather than a function field. Okay, that's the first thing. So this first shuffle relation which I proved and universally in A. So now I'm changing A in a sense that universally in A for a given Q. So I fix a Q and take any function field over FQ. So genus I can change, okay, but it's universal. And I'm going to write it down because it is striking that you will see. Okay, let me just, so I proved it giving an algorithm to give this. Then it was made explicit by my student Lara first, and then by my previous student Chen. And Chen got the most nice formula, so I'm going to write that down. Okay, so Chen's formula, and it looks, you will see that it looks like some formula you already saw here. So zeta A, so this is Chen's formula, Yuzheng Chen, H.J. Chen. Because just saying Chen, I think will identify 3 million people. Mathematics, so zeta A B, zeta A, zeta B, minus zeta A plus B, minus zeta B A. So this should be 0 classically, right? So I am saying that this is summation -1 to the A minus 1, J minus 1, A minus 1, plus -1 to the B minus 1, J minus 1, B minus 1, times zeta A plus B minus J over J, where J is over 0 less than J less than A plus B, and Q minus 1 divides J. Okay, so I just want to make some comment. Actually, this looks like a sum shuffle. Sorry, and I forgot zeta AB. Right, so this looks like a sum shuffle part. This looks like some kind of integral shuffle part, if you remember the formula like that. But this is not 0, this is zeta A times zeta B. So what did I write here? Zeta, yeah. So, I mean, if you just drop this is like sum shuffle, and this is like integral shuffle, but the whole thing is a shuffle. Okay? And it's all coefficients minus where everything is in FP. So this is over FP. Is a sum, in other words, I can say linear combination over FP. Okay? But Q minus 1 divides J, and J is between this and so. Yeah, that's right. This is a strange, this is a different condition. And this signs may or may not matter. I mean, I'm just saying it's analysis. I have not figured out. It's just a different phenomena, but this works in every thing. So what is the consequence? That means if you are interested in algebraic relations are polynomial relations. So those are linear relations in monomials, but the monomials are sums. So polynomial relations become linear relations. Algebra becomes linear span. So that is enough. I mean, classically the same story, but they have 2 shuffles. Here I just have 1 shuffle, and we did that, right? So now we are interested in the linear dimensions of the linear span of this thing. And there are very strong results which I will state then. But now I want to say that these are not the only relations, right? This is the first thing. Then I proved something like Euler's relation, which I will write down. Yeah. Any question? Where is the eraser? So the Euler's type relation, I will call it, and this is now very specific to FQT. So these relations are universal. The next batch of relations, which are actually function field relations, linear relations, those are very complicated and they depend on the field. So I did something in higher genus too, but today I'm just going to talk about FQT story. And the relation is zeta 1 q minus 1 is zeta q over t minus t to the q. So now you can see there is coefficient came out. So in particular, classically the multi-zeta sometimes are same, different multi-zeta. One of my conjecture is it never happens in function fields. There are always non-trivial function field coefficients doing that. So depth is defined in some sense if that conjecture is true. So I conjectured that there are no relations over Fp or Fq or Fq bar. All relations have to have Fqt. That conjecture is still open. Okay, that conjecture, but it has some consequences which I'll say. So okay. So what I want to say is there are Fqt relations. So you want to know, so the weight, so what are the dimensions of the weight spaces? So dimension dw for the span. So this is the dimension over k bar of mzv's of weight w. So this is like, we want to see what is like a Zagier conjecture and so on. So my student George Todd, in his PhD thesis, he worked out just like Zagier did. Zagier used Parry and he did LLL method to find out what are the dimensions. So he had to develop his own LLL method because it was not ready-made developed, and he had to do it for every q. See, there is analogy, there is only one q, and there are infinitely many Fqt, one for each q, right? So you have to guess things for every q, and sometimes that is difficult. This actually, I would say, why this was almost very difficult, so I want to just make this point. This we did not guess. Why? Because we are in character Fp. So this depends on P. These binomial coefficients vanish. There is Lucas theorem. It depends on the Q expansions of these digits of these numbers in a very subtle way. So many of these terms are not there. These are zero. This doesn't happen in number field case. So, and for it, the Q dependence was very hard to guess numerically, right? So these kind of things happen. But George Todd, my PhD student, he had so I had first of all shown that dw is actually, there are no relations up to weight q minus 1. So this is 2 to the w minus 1 for w less than q minus less than equal to q minus 1. And I had a conjecture that there would be no relations. I mean, so this was a conjecture. Okay, so I had to, so you will see more and more. This was first a conjecture, and then this relation is there. So I had 2w minus 1 for w is equal to q. And then the recursion relation is dw minus 1 plus dw minus q. This is Todd's recursion relation. So this he conjectured that from the numerical things that this should be the correct dimension. If you compared with Zagier, Zagier says dw is dw minus 2, not 1, plus dw minus 3. Right? So instead of that, now it depends on q. And this, so this is long. So, okay, I forgot one more thing. Just like we gave Anderson and I, then I had another paper when I defined this multi-zeta values. We had another paper which showed that this multi-zeta values, all of them, are periods of iterated extensions CS tensor S1, C tensor Si, and so on. So there is a motivic interpretation of as a period, motivic periods of C tensor Si successive extensions. So mixed C tensor Xi iterated extensions. We do not have any iterated integral formalism to give a formula like you guys wrote down with differential forms. But in terms of motives and extensions and everything works perfectly. As I said, it's a motive, so there is a Dirac-Betti comparison, and everything works at that level perfectly. So because of that, again, there are transcendence theory and the Grothendieck conjecture, which we know. So this is the Grothendieck analog, Grothendieck period conjecture analog. It's a theorem. Because of that, Chang, I mean, you have to do the transcendence, develop the thing here. So Chang, so first I will say Chang. Oh yeah, I did not say, I should write some names here. So this was Jingyu I wrote. This was done by Jingyu and Chang and Jingyu. By the same algebraic thing, but more transcendence. Chang and Jingyu, Cheyu Chang. Then the Chang also proved that MZV linear relations, MZV weight preserves, relations preserve weight. And all MZVs are transcendental using this motivic are transcendental. So, and our motive interpretation is explicit also. So you can express things in terms of multi-logarithms, multi-polylogarithms, right? So multi-polylogarithms were sort of systematically developed by Che-Yu Chang, and you can also talk in terms of coordinates of this thing. Ooh, I have to. Okay, so this is known. So Zagier conjecture. So then I conjectured. So I conjectured a basis. So I conjectured a basis. So I don't have time to say what that is. And all these conjectures were proved. So I got email on the same day from 2 different groups. It was very funny, totally independent. So I'll write down. First one is Im, Kim, Lei, Godak, and Pham, this group. This group was in France. And another group is Che-Yu Chang, Chen, and Mishiba. I think who is Furusho's student, right? Mishiba is your student, or no, not your postdoc probably, or something. No. Okay, all right. So these 2 groups proved this conjecture. They proved my basis. So okay. So first I should say the main credit goes to Godak. The reason is he first proved that my basis, which I conjectured, spans it. So that's the analog of Brown's theorem, right? So the analog of Brown's theorem, he proved it using, so Todd already had conjectured some kind of combinatorics, how it should imply this thing, right? But it was too complicated, but he could handle it, and he could show that it spans it, and he could show that there is some linear independence in low dimensions. But then this technology kicked in, and both groups, as I said, gave me on the same day, they announced the result. And I should say that this group had the preprint ready, this preprint ready in a couple of weeks, but totally independent. If you look at their preprints, there are totally independent results. Okay, so this thing is now known. Okay, so now when I say motivic interpretation, the way it works, so I want to again connect to some things which were mentioned here. So way it works, so what do we do to do this motivic interpretation? You can look at curve cross itself. So that's the surface. You produce a function, algebraic functions. So either curve cross itself or cyclotomic cover cross itself. Okay, so it's a curves, the surfaces of cyclotomic covers cross itself. So we produce really algebraic functions. So one single function, if I want like a zeta, so I will say it in very rough terms. If you are looking at a gamma function, it's a product over degrees. If you look at zeta function, I can sum over degrees, right? So graph of Frobenius power to the dth degree of the same, if you restrict this algebraic function to the graph of Frobenius power to the degree, so then it becomes a function on the curve. It exactly gives the degree d term of the zeta value or the gamma value. And once you do that, so it's an interpolation kind of technique by algebraic things. Then by T motives machinery of rigid analytic trivialization, what happens is the analytic values of transcendental values like zeta values and gamma values become the periods. Okay, what are these motives? These are exactly Fermat motives, Fermat Jacobians, I think Nakamura was talking about. So we have analogs of Fermat Jacobians, which are T motives with complex multiplication by cyclotomic fields. Using them explicitly, we get this, and there is, so I did it sort of differently, and then Greg Anderson said soliton theory. So what is this soliton business? Because of the connection between the Drinfeld dictionary, there is a Drinfeld modules and Krichever modules using differential operator. If you use this dictionary, Greg Anderson said that some of the things I was doing is like the tau function technology for Krichever modules, which Japanese guys had developed, and then Greg Anderson redeveloped things again. And now I want to come to the, one more thing, and then I will come to the Ihara power series and the étale side story. So one more thing is, so not only we have this motivic lifting, so that is motivic lifting means basically these values somehow have incarnation in 2 variable functions. So there is a motivic function, when you spatialize, you get this thing, right? It's very similar to Brown's thing in principle again, but that's what we produced. There is another lifting because we, so this is now another student, PhD student, she. So let me write this down. So there is an half algebra we constructed, and it was very funny. It was constructed completely by guesswork and by just guessing. So shu he she. So there is an half algebra. I can tell you what conditions. And actually, I should have made 2 slides, but I was too lazy. But anybody wants to see, I can just show you exact half algebra there. But it is commutative. Not co-commutative, and associativity and co-associativity was so hard that it was conjectural. So now these are, by the way, dimensions. As I said, these dimensions over k bar. I conjecture that over fq bar, this dimension is full dimension. There are no relations. If that conjecture is true, that half algebra is associative. Okay. So that is easy to see, but so there is a map from this half algebra to the multi-zeta value linear span, and what that means is not only we have motivic lifting of this kind, but there is another lifting of multi-zeta values to algebraic functions to functions on some pro-algebraic group. So we have 2 kinds of liftings, very, very interesting structures, and this half algebra. So this was first, as I said. Everything was written, but we could not prove associativity and co-associativity. So that was conjectural. Associativity, so this is conjectural. And again, the same group of people have now theorem. So conjecture became theorem with this is a 100-page paper on the archives, still not published, yeah. Not, it's a commutative, not co-commutative, I think. There is also dual, so we'll talk about it later, right? Yeah, so I have exactly what it is. I mean, so there is this one and dual, and we'll see which one is which, right? So if you look at the algebra structure, it's, yeah, anyway, so I don't want to get into that right now, but I can show you exactly what this thing is. And this is on archives by the same group. They seem to have verified associated and co-associated. So in her thesis, she verified it on computer. So we knew it was true. We checked lots of cases and we knew that it was true, but we couldn't prove it, and it is proved. So now I want to talk about Ihara power series. So half algebra I talked about, Ihara power series. So I want to write down one theorem. Okay, I barely have time, but let's see. And that I think, yeah. So theorem, this is Anderson and myself. And this construction, of course, is Anderson's, but using lots of things we did together, Anderson and myself. So this is only for FQT case. So you take a V a prime. So V a prime. GK is the absolute Galois group. Then when we get an Ihara cocycle for sigma belongs to GK, absolute Galois group, we get Ihara cocycle, which now belongs to this big completion. It's not ZP, it's AV. It's a countably many copies of ZV. So Iwasawa theory is complicated. Z star, that's the Ihara power series of one variable. So in Nakamura's talk, we saw there was a beta sigma and there is a gamma sigma. So we are directly doing gamma sigma. So gamma sigma was a refined thing. And in Nakamura's talk, we said that we had to go up to the hyperadelic thing. So we had to extend constants. We don't need that. We can do it at just the p-adic thing or adelic level. So there is an advantage in the function field case. I sigma, the cocycle. So what is the cocycle property? I sigma is the same thing. Z is I sigma to the Karlitz module, cyclotomic character twisting. So I'm not going to define any of this thing. And because of time, I will just read it off. I will just say that this action is so interesting that this power series also interpolates all these Gauss-Jacobi sums in a towers. Now they are using at V-adic towers. So this is like a universal Gauss-Jacobi sum. So if you look at the Frobenius P, where Frobenius P is not sigma, then you get a Gauss sum. If you evaluate this thing at a Frobenius P, you get a Gauss sum over P. The coefficients, you can recover Deligne-Soulé cocycles, which I said connect with these extensions which give you the iterative extensions which give you zeta values. They also connect to the cyclotomic module, which comes from the cyclotomic theory I talked about. So the Deligne-Soulé cocycle and all these things, so that the DS cocycles, zeta cyclotomic connection. And universal Gauss-Jacobi sum, universal interpolation, Gauss-Jacobi interpolation on the tower. So in other words, what Nakamura mentioned in his talk can be completely done slightly better because you don't need hyperelliptic. So there you can do beta and so on also. And that I would say the étale story, meta-abelian story, right? Because this becomes homomorphism. So this gives you a big Galois representation in this valued big Galois representation over the cyclotomic field, right? Because this thing becomes trivial. So it's a huge Galois representation which you get. It is the way it is made. It's you put all these solitons or Fermat Jacobians in a tower. So very similar in philosophy to what Nakamura talked about, but in details it's completely different. Okay, I had to omit lots of things, so let me just say. So I would say this, that there is no Borel kind of K theory, but still we have lots of things. There is also a periodic interpolation which I defined. So there are two types of multis. So Furusho is the main expert on the periodic multi-zeta values. So I want to mention this. So I had defined periodic interpolated values. Okay, they for all p's and so on. And of course there is a motivic values, because motives, if you instead of the Dirac-Betti period, if you take crystalline periods, you should get some kind of periodic things. And Furusho, Deligne, Jarose had various constructions of periodic multi-zeta values which are different, but the spaces were the same. And Chang and Mishiba again developed using Furusho's ideas about the multi-poly logarithm, and they concretely developed whole periodic multi-zeta values. So my student Chibin Shen, in his PhD thesis, he looked at the relations between the interpolated ones, between the for the motivic ones, the relations are clear. The dimension is as usual. So dimension, so dpw is just dw minus d, w minus 2 there, but here it's q minus 1, right? Because q minus 1 is like 2. So that because they're the same relation, and you add the relation that zeta at E1 for the periodic things are 0 because of trivial zeros of Riemann zeta function type things, which is true in function fields also. So on the other hand, the interpolated ones are different. Okay, the dimensions, we have some conjectures, they are different. On some subspaces, we can write them in linear combination of each other. So there is some analog going on some subspaces of multi-zeta values, not everything. We can prove that there are no relations at certain level, and certain level there are relations. So it's a very mysterious thing. And I would like it, classically, I'm sure a similar thing is going up. So Sinan Unvar had done some work which I looked at in depth too. So this is probably something connected to that. It would be very nice to understand what is the connection between the interpolated one and the motivic ones. Third thing, you can look at the finite variants, which means, so these were looked at, so this again was looked by my student here. So he had some conjectures about universal relations. So it turns out that these spaces are different, interpolated ones and the periodic ones, but there are some spaces they agree. We have conjectures about the dimensions of these things. And there are some universal relations. That means they work for all large V, large degree V. And that is conjecturally characterized. We cannot characterize yet all the interpolated relations, but we can characterize. So those relations are universal. They work for motivic ones, also interpolated ones for large V. Okay. And there are these finite variants. So these are, I don't remember the notation, the zeta. So the Z, maybe I'll use ZS1, S2 is, something like you look at, you put some mod degree P is less than or equal to degree A1, degree A2, and you can do several things, but 1 over A1 to the S1, A2 to the S2, and you look at mod P, and you are interested in the relations between these. So these are just rational functions, but you are interested in the relations which work for all large P. So you are looking at the universal relations. That's like direct product divided by direct sum, right? So this is the finite variants. Classically, there is a work of Akagi, Hiroshi, and Yasuda, which express these things in terms of periodic. That doesn't work in our case. And the dimensions are again different. And again, on subspaces, something is happening. So I would like really to know philosophical reason. I mean, philosophical means structural reason why this kind of things are diverging from the classical case. Okay, so this I wanted to mention and get something from Furusho. So for example, we have conjectures for the dimensions of these. And because of my Euler relation was proved in a certain way where it mixes some dimension, it follows same recursion formula as Todd, but the initial values are different. than the p-adic ones. Okay, so that means it diverges completely. But the recursion relation is the same for some reason. So there is something very interesting going on structurally. That's what I want to say here. So finally, I will take a couple minutes, and I want to say we also looked at the colored variants. So main question is, what is, this is the linear version in your language. What is the profinite? What is the version? Is there some kind of MGN? Are there some spatial functions which you can do in elliptic polar logarithms? Elliptic polar logarithms is possible, maybe probably with analogies, but are there some MGN function theory which we can do in function fields? All these kind of questions are fascinating and open, and I just don't know. And then, of course, what is the K theory? There are X groups. So X groups are moving. So we are getting more and better results. So I will just say this. So the motive, so mixed state motives category is not completely defined. But if you look at the mixed MZV category, which we, so those are the extensions which we used, I have a reason to believe that. So there is, okay, so I want to say that, so classically there is a there is a central GM multiplicative group, and pro-unipotent part has Lie algebra, which is generated by one generator in each odd dimension, right? I claim that, so it seems to match with the calculations that we have similar situation. Now the Lie algebra has generator in each dimension not divisible by Q. So this is strange because the analogy was 2 goes to Q minus 1. Now I'm getting Q. Okay, but that exactly works. And so for some reason, the central GM is, I have to kill that off. So that is like p-adic case. So if it's a non-Archimedean case, it works. But so I am talking with some expert. I will also want to talk with you on that, about what's going on here, because 2 pi I is transcendental, just like in the number field case. But somehow, like p-adic case, it's going away in the central part. So the structure is such that only we'll get a pro-unipotent part, and then it matches, everything seems to match beautifully. This is just, I just want to say it, there is no theorem written on that yet. So having said that, I want to end by saying that there are 2 approaches, as we saw, as he explained, there are 2 approaches to understand the absolute Galois group of Q. One is by linear representation, Langland's conjectures, and one is the Grothendieck nonlinear approach, as he said. So for the Langland's conjecture, Drinfeld developed Drinfeld models, right? Drinfeld did the Langland's conjecture eventually. We, rather than looking at the moduli and what Langland's program, we looked at the arithmetic of this, and somehow we ended up with the linear version of the GT approach without having GT. So that I find very interesting, and I will end on that. Thanks. So I will just say that lots of things I just said. There is my book where is many of these things are there, and later things I have this survey article, so I can give a reference, and it's half algebra. Anybody wants to see, I can show you exactly what it is. And most of the things are already in the archives or published.
Yeah. So any questions or comments? Yeah.
Sure.
So I think you don't have a motivic fundamental group in positive characteristic. Unipotent fundamental group in positive characteristic.
Say that again.
Unipotent pi 1.
I'm just saying.
So that's why.
I'm just saying analogy. I have never understood the complete. I'm saying that this is like the unipotent part story.
Yeah.
And I have something like which has the dimensions work in such a way, which I said.
Yeah.
Whether it is called unipotent and so on, I have not even studied that language.
So okay? If you don't have a unipotent pi 1, then
No. So we don't have pi 1 at all. We don't have the pi 1 story at all. What I'm saying is, it is work. So what you called unipotent pi 1 in the number theory game, we have an excellent analog of that. Okay. There is no pi 1 itself, as I explained first, right? It connects to the prime field rather than a function field. There is no function field Belyi. If you have something over a function field, you want to do.
It's a profinite setting, is that?
Sorry?
So Belyi's theorem is a profinite setting.
It's a finite setting, right?
So I'm talking unipotent set.
No. So what I'm saying is there are lots of differences. So we don't know what the correct object is. But somehow the analog of the correct object at the pro-unipotent level is there. As you can see in the meta-abelian story with the Ihara power series, and you can see the Dirac-Betti story in the multi-zeta values. That is working beautifully. Okay. Tanakian category. This is all done by using Tanakian category. So the yes. Oh yeah, the motivic Galois group is the main tool, right? But we don't have some kind of topology and or those kind of things.
And so your series, this Anderson Thakur series, is this your?
This is the Ihara, I for Ihara, right? Ihara power series.
Yeah, so function field case.
Yes, this is function field case.
So is it analog of your gamma function?
Yeah, exactly. It's a twisted. So it's see the gamma function I defined it was a gamma function. Then you have to put. I have two gamma functions because there are two cyclotomic theories, right? So this is the Drinfeld side of the gamma function. You put it in a tower, and you use the Coleman's technology of going from norm-compatible things to the Galois compatible things. And that's how you get the power series, right? Now you have to do, it's technically much more difficult because as I said, instead of finite residue fields, you are having a big residue fields, which are transcendental fields. But Anderson developed it, the Coleman power series technology for that. So these gamma function things, we can put it in a tower, twist by Galois. Everything you do algebraically using Weierstrass preparation and so on, and periodically, and then you twist it and divide as usual. So what Nakamura wrote down the formulas, there are analogs of that by putting things what we did. Okay. Yeah.
Can you explain again why is transcendence not hopeless in that case? Not even not hopeless, but for instance, why is this injective?
So why does transcendence work?
Vaguely,
you're asking why the transcendence works?
Yeah, why does it work?
Yeah, so I can say something about that. The periods, the whole setup is such that the periods are governed by functions which are like E functions in transcendence theory. Classically, this doesn't happen. So that's why we have more control. Okay, and this was done by this Anderson, Brownawell, Papanikolaou. And this is like Szydlowski's theorem in a classical case, but that just doesn't apply in classical case. And here that this was done before that. So this is totally independent. They did it afterwards, but this is done. So there is some setting where this technology just works exactly to give periods. And there is a Tanakian category is used. How do you prove the transcendence result? You look at the periods, which motives they come from. You look at the motivic Galois group and you calculate its dimension. The dimension is the transcendence degree of the periods. And so you have some, and then it matches. So you have some relations which are known, and then if it matches, those are the only relations. That's how all these results are proved. Okay.
Which is hopeless.
Which is right now hopeless in the function number field case because you don't even know irrationality. The transcendence is very hard because the technology just doesn't apply. So these motives are great. See, the motivic technology is philosophically very well understood in number field case, but the Grothendieck period conjecture is open. Even the Tanakian things are open because of standard conjectures are open. These motives, there are no cycles or K-theory, but they are directly motives where the other things work well. Okay, so the motives have the realizations and so on. Well, you don't need K-theory or so on. There is extensions of the motives themselves are a substitute for a K-theory. So some things are missing, but things which work well are like that. And higher things, you again need some stukas, so higher genus things. And there is even there are a lot more to story. I just mentioned things which are connect to GT, what we heard. There is much more to the story.
Okay. So may I ask? So there is a Grothendieck period conjecture in the characteristic case, or
I should not say. In the function field case, right? The characteristic P is a global function field. That's where we are, right?
Yeah. So there are periods.
There are periods, right? There is a motive, so there are comparison isomorphism. There are periods.
So, can you say that these MZVs are periods?
Say that again.
Can you say that these MZVs in function field case
that's what I said, right? I said that motivic periods. These are motivic periods. All MZVs are motivic periods of the successive iterated extensions of these pure motives. These are like Z, Tate. So this is mixed state motives.
Okay. But then how should we understand that these are periods? Because usually you think that these are iterated integrals. So
that formalism
you want
is
to
but there is a pairing between the DRAM and Belyi. So instead of calling, so there is no integration theory which gives you this pairing explicitly. But there are other things you can do. You can solve some Frobenius difference equations rather than differential equations. So that is the substitute for integration.
So
okay,
it
so
means
there
that-
is no well-developed theory of integration where I can just write down a formula, but in the background is there in motivic terms.
So you say that MZVs are special values of polylogs, and polylogs obey differential equations. And then that would be.
There is something like that also.
Replace
So
the differential equations with difference equations with Frobenius. Okay.
Yeah. So there are polylogs are there, but okay. As I said, there is a difference between this itself. So classically, what is a polylog? You have z to the n over n to the k. This doesn't make any sense if both are polynomials, right? So there is a mixing of n and polynomials going on. Okay.
Yep.
So polylogs, when you say the value at 1 is zeta k, that just doesn't happen in function field case, right? Because it's not that. So there is a linear on the other end, but somehow see that's the beauty of these analogies, Rosetta Stone, which Andre well mentioned, that some things are just totally different, but somehow at the main end results work out.
Okay, so
it's a linear combination. The multi-zeta values are a linear function field linear combinations of polylogarithms at algebraic arguments.
Okay, and so could you give an example, for example, of this analogues of the polylogs or that exist in the function field case?
Sure. So I erased that, but there was exponential, right? I mentioned exponential. So if you have exponential, there is inverse function logarithm. So logarithm has coefficient z to the q to the I divided by li.
Okay, so
that's a logarithm. You put li to the k, that's polylogarithm. And then you order i's, that's multi-polylogarithm.
Okay.
It's as simple as that.
Okay. So can you say it again? So you have the invert exponential. So can you write?
Sorry. So exponential z looks like summation z to the q to the I over di. That's the standard notation, right? These are function field coefficients. Then I have logarithm, which is the inverse function. It will satisfy a functional equation just for the same reason. So this will look like z to the q to the I over li. Okay. Then I can have multi-logarithm ln z, which is z to the q to the I over li to the n.
Okay.
Then I have multi-polylogarithm ln1 to nk. I mean, you can use multi-variables or one variable and so on, but the denominators are basically will be I to the n1, li1 to the n1, lik to the nk, and you just put some order here, right? And these multi-polylogarithms, the linear algebraic linear combination of those, you can express those things in there. And that comes from this motivic expression. So this motivic expression itself has a logarithm of this, which connects with this multi-polylogarithm. So once you work it out, you get an expression in terms of multi-polylogarithm if you want.
So your main point is that all these functions satisfy a bunch of differential equations.
Differential equations
with respect to Frobenius.
Frobenius difference kind of equations.
Okay.
Yeah, exactly. Okay. So it's like Lang isogeny pull back kind of things going on a lot in Stukas and here.
Okay, understand. And that's why then you take their particular values.
So the main differential equation, main equation is like that. There is a matrix which gives you a t action. There is a t and tau, right? And then you solve. There are two copies. Those two. I mean, I said it's a function curve across another curve. So there are two copies going on. In one copy, you twist by Frobenius. And you specialize. So it's a graph of Frobenius you are twisting, and you are solving the equation like C phi kind of thing. So this comes from T action. You solve this equation. Entries of these things are periods, and this is all happening in a Tate algebra. So there is analytic things going on, but algebra is controlling it completely term by term. Terms are graded by the degrees. That's sort of the mechanism.
I see. Thank you.
Very naive thing. The shuffle,
Yes.
the first shuffle usually comes from the iterated integrals. So
Thank you. I had to skip so many things. Let me just take 1 minute and ask Furush. I wanted to mention this to Furush thing. So I wanted to ask you around about étale, here some philosophy about double shuffle, and I was interested in this because we have, this is one shuffle, And I am thinking there should be another shuffle, and maybe the similar thing goes on. The other shuffle, on the other hand, will not be depth preserving, unlike the classical integral shuffle. That I know. It will have function field coefficients rather than the integral coefficients. So it's hard to guess, but I hope, yeah. So, okay, sorry. So now let's go back to your question. What was your, yeah. Sorry, I just, because yeah. This is one of the things I dropped because of the time.
No, the philosophy, the classical philosophy, that you have the continuous part and the continuous side and the discrete side.
Right.
So you have integrals and.
Yeah. So the integrals are coming through the motivic formalism. That's how I'm thinking.
It simply means that if you subdivide the simplex, if it's continuous, the boundaries of measure zero. If it's discrete, the boundaries.
Yeah, but we don't understand the topological understanding of these things at all. So I want to tell a funny story. So I just took an opportunity of using your question and making more comments. So this happened at TIFR. I remember Bogomala was talking, and he went over like half an hour. So finally the chair cut him off and said, okay, let's finish. We are over time. And he says, any comments? And Bogomala says, I have several comments. And he continued for 10 more minutes. So I pulled out something like that for 1 minute. Sorry about that.
Yeah. If there is no further questions, and if you yourself have no more comments, then let's thank the speaker.